Hello, everyone. We are excited to present a realistic approach to combining renewable energy resources to generate power and directives. And that directives involves from agriculture to pharmaceutical industries. So we evaluated our value propositions through economic metrics such as net present value and levelized cost of energy. I'm Shah Kabir, and two of our investigators are here to join me, and that Jose Benavides and Pushpa Sharma. So, what motivated us? Well, we found that the solar day cycle can be juxtaposed with the night cycle of thermal energy extraction by wellbore fluid circulation in a wellbore to manage excessive cooling. And we'll get into those details later, but I'll just get capturing the headlines. So that's the game plan. We want to have then evaluate all those methodologies with the technical and economic metrics. And we have the directives for pharmaceuticals and the indirect use for power generation and good prospects. So here's the future outlook that you can find in various settings. The oil and gas is still dominant, is marked in dark blue, and the low carbon emission solutions are coming in, as indicated in green. And so it will take time. So we cannot just turn off the switch and go for green energy revolution, so to speak. So here are the real prospects in the U.S. In some of the western states, as you can see, that we have a high geothermal gradient, whereas most of the states are not blessed with that outcome for the same depth, that is. So it is at a lower level, so we can generate, in simple terms, in the yellow states, we can generate hot water for direct use, whereas those in the red states we can generate steam and therefore power. So these are the two methods for interest. One is the fluid circulation in a wellbore. We circulate fluid down the annulus and up the tubing, and it's a closed loop system. Only heat transfer occurs, but the heat transfer rate is very slow, so if we are circulating for a long time, then it cannot keep up. So that management becomes an important issue. Now, in terms of solar, you can see that there's evolution is ongoing. The smart flower is way more efficient than the regular solar panels, but they are expensive. But the underlying point here is that they are only operational during daytime. So what we do here, just to go back for a moment, that we do the modeling. It's a numerical modeling, so stepwise modeling to preserve our mass and heat balance. And so that this is a numerical approach, whereas the heat flow from the formation, we use the analytical approach. Okay, so now let me provide the overall vision. Here's the thermal plant involving the closed loop fluid circulation and wellbore, where the heat exchanger. So this fluid, circulating fluid, can be pentane, CO2, or water. And this is a heat exchanger, and then we generate steam and put it in the turbine to generate power. The let me explain that a little bit better here. So we are creating also a natural gas source for the simple reason that we want to have a backup plan, so to speak, because should something happen here in this sector, power generation, or for that matter, the solar that we are bringing to the table. So yeah, we have cloudy days, rainy days, so then it'll be difficult to do that. So that's why the backup plan. So we are considering 25% of our energy source coming from this natural gas plant. And so then it goes through the transformer onto the grid. So now I hand it over to Jose Benavides. Thank you.
The big disadvantage of producing energy by continuously circulating fluid in a closed loop is the significant decrement of the geothermal gradient in a small amount of time around the well. To overcome this issue, we propose an intermittent circulation with periods of circulation and non-circulation. This way, the geothermal gradient is not significantly affected, thus the energy extracted from the well will be much higher. To compensate the lack of energy during this shut-in period, another source of energy will be implemented. For instance, a twin well or a solar panel. This graphic shows the intermittent approach using twin wells. The wells are located at a distance that interference between each other is null. By producing energy from two wells at different periods, we are providing a constant energy flow and conserving the geothermal gradient, which is ideal for indirect use. It is evident the huge difference between the intermittent and the continuous flow with respect to the outlet temperature. The same trend is followed by the power generation. The main message here is that the twin well approach is most efficient for energy extraction. In the previous slides, we have shown the potential way to improve the energy extraction by circulating in periods of circulation and non-circulation. But what about the fluid? Another way to improve the energy extraction is by selecting an adequate fluid. After evaluating different fluids, pentane proved to be the best option. It overcomes water in terms of energy extraction, being ideal for indirect use in regions with high geothermal energy. Now that we have seen the technical side of this project, let's dive into the power demand and supply. The average annual power consumption of a family house is around 10,000 kilowatts per hour. The power output of an intermittent hybrid plant of 10 wells might feed over 700 homes, and by hybrid I mean the combination of three different energy sources: thermal, solar, and natural gas, where natural gas production of energy would be at a specific percentage coming from the total energy of thermal and solar. In a bigger scale, 12,000 wells would provide energy to a big city such as Houston. In the next slides, we will see the economical analysis which will be covered by Dr. Sharma.
Thank you, Jose. So I'm going to talk about some of the economic implications of the geothermal application. So in this slide, we are talking about a 20-year NPV for a thermal and solar combination for an intermittent cycle. So intermittent cycle, we mean 12-hour injection of geothermal and then 12-hour of solar potential. So here we have 20 duck well versus 20 new wells. Duck is drilled but uncompleted wells. So where the well cost assumption is $500,000. So you're not drilling a new well, you are just using the drilled well, but you have to still do some work over to make it ready for geothermal. New wells, we are considering a $3 million well cost per well, where you're drilling a well from beginning. So if you look at the comparison here, with the carbon tax of $150, you will make $1.2 million in 20 years for a duck well. And if you're using a new well, you stand to lose $1.3 million. So there is a significant advantage of using a duck well for geothermal development. Now we wanted to scale up this scenario, and we wanted to explore how this scenario will look like when you apply it in a bigger city, like a city of 900,000 homes, which is very similar to what situation we have in Houston. So here because in a bigger scenario like that, you cannot only rely on thermal and solar. So we added a third hybrid option, which is combining it with grid or natural gas power. So when you have grid, that means the thermal and solar is getting some benefit out of the grid, so it can exchange electricity from the grid. Or also in other scenario, you have a natural gas system with your thermal and solar power, which is providing energy to meet the demands. So in both the scenarios, to have a fair comparison, we assume 25% of the energy demand is driven by grid in one scenario and is driven by natural gas in another scenario. So if you look at the NPV comparison, the numbers are very similar. You stand to gain around $1.5 million in both the cases. And similarly, if you go to LCOE, the grid scenario has a higher LCOE of around 13 cents per kilowatt hour, and if you look at the thermal power, it's it's around 9 cents per kilowatt hour. Here also we assumed a $150 carbon tax. Moving on to a completely different scenario where the geothermal energy is used for direct use. So where instead of generating electricity, we are utilizing the hot water or hot fluid directly to supply to our industry. So here we wanted to compare different fluid scenarios. So we compared pentane versus water. And as you can see, we tried different approaches. So we compared continuous versus the intermittent. Continuous is non-stop injection, and intermittent is 12 hours on and 12 hours off kind of injection. So if you look at the plot for water, water was continuously decreasing starting around 80, and it quickly goes down to very low temperatures. So it is not a very good outcome for the direct use. If you change the same water but intermittent injection strategy, you start to see a very high level of temperatures. You can start around 80 and then you can maintain around 75 degrees C for almost 20 years. But a better scenario is when you start using pentane. Pentane, you will start around 100 degrees C and you can maintain somewhere between 180 to 20 years scenario. So with these kind of different fluid combination, you can see there is a lot of potential in different industry. So you have food processing industry, which is looking for 60 to 75 degree water, and then you have different ranges. At the higher range, you have 90 to 110 degree in the concrete plant. So there is a good potential of direct energy, direct use for geothermal. So now if you talk about economics implication of a direct use scenario. So in the direct use scenario, if you consider a 20-year NPV for intermittent circulation, if you take a water scenario, your NPV is around $2 million. And if you go to pentane scenario, your NPV is around $7 million. So it's with 30 duck wells for a 20 well scenario. So again, we use duck wells here, which I mentioned in the last slide. It's drilled but uncompleted well, which the well cost is only considered to be $500,000 per well, and the carbon tax is also considered to be $150. So there is a significant value if you find use for direct use of the hot water. There is a better value proposition for geothermal energy. So in conclusion, the major finding from the study was that cyclic fluid circulation strategy involving night thermal and day solar appears technically sound. It also appears economically strong, as we showed in the previous slides. When we talk about thermal solar hybrid for a bigger application such as a city like Houston, you have to have a hybrid approach with the natural gas benefit. So that strategy is economically attractive, and it also makes sense because you have additional cushion in case of any disruption in solar or thermal. You have natural gas to make up the energy demand. And the last point is that as we talked about direct energy, so there is a huge value proposition, huge value in utilizing geothermal energy for meeting the energy demand of different industries, which is agriculture, food industry, and that can work in a low geothermal gradient situation. Now, thank you so much for your time, and we'll love to take some questions from the audience. Thank you.